Welcome everybody to the AI Institute Distinguished Lecture Series. It's a pleasure to welcome back Professor Alan Kaptanoglu. So Alan did his PhD here at University of Washington. I was just thinking back, I'm pretty sure we had our first research meeting when I was in an airport flying to India the summer before COVID. So you joined right before COVID. Did a ton of great work moving kind of sparse nonlinear modeling over to plasma physics, which is a lot more complicated than incompressible fluid flows. And after a relatively short postdoc, Alan joined the faculty at the Pratt Institute at NYU, one of the premier applied math institutes in the world. It's really a pleasure to have you back, Alan, and take it away.
Thanks, Steve. I really appreciate that. Yeah, I'm gonna try and keep this relatively brief, around 30 minutes. If I go over that, just shout at me because I'd rather have time for questions. And really, this is just sort of an advertisement about things I've been thinking about. Hopefully, we can talk about it after and share some ideas on this stuff. So you know that yeah, Steve, Nathan, other folks here, they work a lot on sparse regression, often in the context of system identification. So how do you identify equations from data, and how do you do that in such a way that you promote sparsity? You promote only some terms or certain terms in the equations that you discover. But this notion of sparse regression or enforcing sparsity is really useful across scientific domains. So I'm going to talk today about how it comes up in something called inverse magnetostatics, which, yeah, sounds very jargony, but you're going to see is like actually a wide class of interesting problems that come up all over the place. And of course, I say that, but then I'm going to zoom in on about the most esoteric place you can imagine applying this, which is designing nuclear fusion reactors in plasma physics. But I want to keep in mind that all these methods are quite general, actually. Okay, yeah, so I'm going to talk about the big jargony words here: sparse regression, topology optimization, and this field of inverse magnetostatics. What are the connections? What do they mean? I'm going to introduce some interesting magnetostatic problems. As Steve said, I work on plasma physics at the end of the day, so I'm going to show how this is useful there. And then show how some of the algorithms we've used for system identification actually can be nicely repurposed, and you can find variants of them that effectively address these magnetostatic problems. Okay, so what does sparse regression mean? So sparse regression is just a general term for optimization problems in which you want the solution to be sparse in some mathematical sense. Okay. So you have a minimization problem over some set of optimization variables alpha. This is a vector of variables. We have some objectives. You might have a long string of objectives that you want to minimize with some weights, kappa, sigma, and so forth. And you might also have some hard constraints you're trying to impose, whether they're, I've written them down as linear constraints, but they can be nonlinear constraints or anything you like. And the sparsity is coming in this last term I've written down. Sparsity can be imposed in many ways, but sort of one of the hardest ways you can do is write down what's called the L0 norm. And the L0 norm just says, it just basically looks at your vector of optimization variables, and just counts how many are exactly zero. Sorry, how many are exactly non-zero, and it's trying to minimize this quantity. So it's sort of promoting as many of those optimization variables to be sort of turned off and not used in the final solution. And there's also a G at the top of that, because often we don't want to just like sort of zero out all the variables equally. We actually might have subgroups in the variables. So the big G here is standing for group L0 norm, and you can do what you want with that. The summer camps have started, I see.
They're really exciting.
Yeah, exactly. Okay. Good. So that's sparse regression. Oh, and yes, so the unfortunate part of it is if you are really wanting to promote this L0 form of sparsity makes the problem really hard. It's non-convex, it's non-smooth. And so we often replace this with weaker notions of sparsity. Sometimes it's called relaxations. And this can be the L1 norm, many other variants. And if you don't do that, if you stick with this hard form of sparsity, often you can't solve this optimization problem exactly or with like strong guarantees. Instead, you solve it greedily. And I'm going to talk in a few slides about what it means to solve a problem greedily. Okay, and I wanted to bring this to your attention that actually there's another field of optimization called topology optimization, and it's quite similar in spirit. This is a super important problem in structural mechanics. It basically comes up anytime you have like, you can imagine you have a structural mechanics problem, like you're building a bridge, and you want to know exactly where the bridge material should go. And the bridge material either needs to be like 0, there's no bridge material here, or 1, there is bridge material here. So it's a fully discrete problem that is like, you either have a sort of full optimization variable set to 1 or to 0. And this is similar in spirit because it looks exactly like the previous problem. You have some other objectives you're trying to minimize, you might have some constraints, but you really impose like full discreteness on the optimization variables rather than the sort of weaker version using the L0, where you're really just like setting certain variables to 0. Okay. Yeah, I think there's some opportunity in the literature to think harder about this connection. This has not been carefully looked at in the literature, and both fields have like really nice algorithms that neither of them use or compare. This is something I want to look at and wanted to flag for everyone here. You may have seen this if you're like a mechanical engineer. This is a very common thing to do in the field. Any questions on those two? Last 2 slides? Hopefully folks have like seen an optimization problem formulated before. This is not too confusing. Okay. And yeah, just like before, if this is a high dimensional problem, you're going to have to relax this or you're going to have to solve it with greedy algorithms. It's still very hard. The non-convexity of this problem comes in the fact that you have discrete variables. So this is really hard. Okay, and so now I'm going to talk about what inverse magnetostatics is and why it's important, why it turns out it looks like these other problems, topology optimization and sparse regression. And the fundamental question of inverse magnetostatics is you have a desired magnetic field that you want somewhere on some compact volume or surface. In our case, we're going to be thinking about we want a certain magnetic field on a compact toroidal surface. And we know what magnetic field we want, but we don't know how to produce coils or current sources to actually realize that field. And so the optimization problem is how to find those current sources that produce the field you want in the first place. And this has tons of uses, designing magnetic fields basically for any experiment or industrial application. If it's a complicated 3D magnetic field, this is the kind of problem you have to solve. And the degrees of freedom are quite complicated. It's like the number of current sources, what their shape is, what their location is in space, and how much current are you putting through. So there's a lot of things to play with there. Okay, so an example is, and this is going to be the one relevant to the plasma experiments I'm going to talk about, is we minimize some, so we have a surface where we want to match a magnetic field. And so we just are basically minimizing the normal components of that magnetic field square over the surface. Okay, and we have some variables alpha that represent the degrees of freedom we have to play with those current sources. Okay. This is going to be sort of the primary term in the optimization. Okay, so like the primary target of sparser of the optimization problem you're going to solve. Okay, and how do you actually compute the magnetic field on the surface you're targeting? Well, at the end of the day, you have current sources. The magnetic field from them is obtained from the Biot-Savart law. The Biot-Savart law tells you magnetic field at a position R given some volume V prime of current sources, and you have to do this three-dimensional integral over those current sources. Okay, and this is also challenging because look what we're minimizing here. We're minimizing a double integral of a triple integral. So there's 5 integrals under the sign here, and you might have to recompute those 5 integrals every time you like mess with the current sources during optimization. So you also need all this to be like really fast and optimized in terms of computing this super fast each iteration. Okay, sorry, this screen sharing thing is in the way. So I can move that. Okay. All right, yeah, so as I said, I work in plasma physics, and there's a class of device called stellarators, and this is a really nice place for thinking about inverse magnetostatic problems. You might have heard of a tokamak before. What this is you have some plasma that's axisymmetric, so it's an axisymmetric torus, and you put some coils around that also have this axisymmetry, and it generates an axisymmetric magnetic field. So that's nice. It's basically a two-dimensional magnetic field because of the axisymmetry. Turns out this works really well in lots of experiments, but actually these devices tend to be really unstable for various plasma physics reasons. And so a lot of people have been experimenting with these 3D magnetic fields associated with stellarators. And you get better physics properties, but you can see you also get a much more complicated geometry, and therefore a much more complicated problem for inverse magnetostatics. So now you have like this super complicated three-dimensional plasma, and you need these super complicated coils to actually generate the magnetic fields that you need on the surface of that plasma. Okay, so I've been working a lot on these stellarators, and they sort of are a really fun test bed to try out a lot of these methods and techniques for magnetostatics. Take a second here. If no one's seen a stellarator before, this might blow your mind. So
How did they come up with this design?
yeah, that is a good question. So they come up with the plasma because there are a number of metrics you can optimize that like make it a really good fusion device. And so there's actually really 2 optimization problems here. You like first really try and find a good plasma shape that gives you good fusion confinement. And then you like fix that plasma and you do this second inverse magnetostatic problem. And you say, okay, given this really good plasma we want, how do we actually build coils for that thing? And there are still a lot of like kind of arbitrary choices. Like when you optimize these coils, you often have to specify like how many coils you want beforehand. You have to say like, I think I want 40 coils in total. And then given that choice, you have to optimize those shapes. Yeah, cool. But there's a lot of like tweaking and playing with parameters and yeah.
Is that what the hidden symmetry, like the hidden symmetry sounds very magical?
Yeah,
the
hidden symmetry is magical. Yeah, so in this case, the magnetic field is totally axisymmetric, so it really is two-dimensional, and that's the whole magnetic field vector is like an axisymmetric object. Okay, the stellarator is interesting because it has a fully three-dimensional magnetic field. Magnetic field depends on all 3 coordinates, but what you want to do with the stellarator is you can actually design a magnetic field such that the B vector depends on all 3 coordinates, but if you take its magnitude, it depends on two coordinates. There's a hidden symmetry that the modulus of B is actually like two-dimensional, and if you look at it in a certain coordinate system.
Okay.
And the beauty of that is that restores all the beautiful confinement properties of having a two-dimensional magnetic field. So there's like a deep theory here called quasi-symmetry, and yeah, it's awesome physics. So yeah.
And then since you mentioned stability properties,
Yeah.
what are the many instabilities or just one of the instabilities that we talk about?
Ooh, where to begin?
Any of them, not all of them.
Yeah, the problem with this design is doing some Ampere's law stuff, you can quickly figure out that if you actually need to drive like really big currents in the plasma in order to like generate the full magnetic fields you need to like squeeze the plasma together and get it really hot and dense. Okay. And the problem with that is that then when you run these things, there's like 10 mega amps of current running through the plasma, which is like an insane amount of current. And that's a huge source of free energy for the plasma to like get some of that free energy and drive instabilities. So the stellator is an attempt to basically literally like helically twist the plasma as you go out, so you don't have to drive this gigantic current.
I see, sort of like riding a bicycle at like 50 miles an hour. It's very stable in one direction, but a lot of.
Yeah, no, I like that analogy a lot. Yeah,
Thanks.
yeah, absolutely.
I have a question on this.
I'm sure I can,
I can give it
yeah,
to
if
you
you,
if you want,
yeah,
yeah.
please.
Are stellarator magnet coils typically single output actuators?
Yeah, I don't have a good answer to this. I don't know how much they're really actuated in practice. These modular coils, typically they just like are fixed to some mega amp level of current and just like fixed like that the rest of the like the entire time the plasma is going. I will show in a second a picture with like often people put like even more coils on the outside, and those they actually actuate during the plasma to like do some extra magnetic field shaping. But typically these like gigantic, like these modular coils, for some sense of scale, can be like in like a full reactor device can be like 10 meters high. They're like enormous things driving mega amps of current. They're superconducting, so you're like cooling them to liquid helium temperatures. I mean, the whole thing is like an absolute really complicated thing to set up. So typically you're not doing any active actuation with these big coils, but you do have to do some like sort of passive control because all these coils in principle are coupling with the plasma and with the other coils. And so there is a little bit of feedback you have to do just to keep the coils like driving the current that you want them to drive and not like starting to drift away because of coupling. Okay, yeah, and I wanted to address this a little bit too. So I showed you these what we call modular coils that basically interlink once with the torus. So that's what I'm showing here. They basically go through the torus once. They can be circular, they can have more complicated shapes, but there's lots of other types of coils you can design. You can have helical coils, which actually wrap around the torus, but can go through the torus multiple times. There's certain advantages to that. Often we have a vertical field set, which if you drive a current in this, just drives primarily a magnetic field like through the donut. And then we can also have saddle coils, also called dipole coils. And that is coils that are not topologically linked with the plasma, right? They're like outside and providing sort of extra shaping. And those we do often do active control. And then so in addition to dipole coils, if you have a smaller device, you can actually use permanent magnets instead. And this is a really fun really fun way to do this because I'll show you in a second, but you can like 3D print these arrays of permanent magnets and use that to shape the magnetic fields you need for these stellaries. But it's similar in spirit to the dipole coils. It's like external current sources that you use for shaping. Okay, yeah, and I'm interested in a lot of these like kind of weirder ideas. There's been new designs in the field for like how do you I should say one of the traditional issues with the stellarator is that these coils are really complicated. So if you just stick with these modular coils, you get these really complicated three-dimensional coils that like often get really close to one another, which means the forces are super strong between the coils. And this is actually a real stellarator that was built in Germany called W7X. And it cost them billions of dollars to make it because they spent all their time trying to assemble and manufacture these coils. And if you misalign these coils by like millimeters, you screw up the magnetic field. So you have to spend all your time trying to align these coils like with millimeter distances. So these things are really hard to build. And so there are these sort of alternative ideas that have bubbled up in the literature. One is to do this purely with permanent magnets. If you can do this with like tabletop experiments. And this was built at Princeton actually a few years ago. Here's like the vacuum vessel where the plasma gets created. And then what they did is they just 3D printed some nylon and just like made some permanent magnet sized holes in these toroidal slices. And what you do is you have like a team of undergrads just like put magnets in holes for a week, and then you bolt all these together, and at the end it looks like this, where basically you have a set of toroidal coils. The blue here are these magnet holders, and the gray here is this vacuum vessel, and they achieved their first plasma a year or two ago. So the plasma is glowing here in this pink color, magenta color. So yeah, what's really nice about this is they built this laboratory experiment for like $100,000, which in the field of plasma physics is like the cheapest thing that's ever been built by far, kind of. So like amazing they managed to do this. And people have been thinking about how do we scale up this sort of thing for like big reactors. And one way you can do it is do something similar, but instead of permanent magnets, these are like rectangular coils. And the advantage of coils is you can actually drive as much current in them as you want. So all these little coils can be driving like mega amps, and you can sort of play the same game. You have like a modular array of these what we call dipole coils, and that allows you to use quite a bit less complicated modular coils. Okay, so I've taken a break from talking about sparse regression. Let's briefly show that like the permanent magnet problem, you can formulate a sparse regression. So the way we're going to do this is we're going to imagine we have our plasma surface, and then we're going to imagine we just have some volume around this plasma where we're allowed to place magnets. And so that's going to be this like green volume here. And so, and we're going to chop that volume up into one big three-dimensional grid and say we can put magnets anywhere in that grid. And so what we're going to do is we're going to say we have a bunch of permanent magnets, which are what we call like perfect dipoles. And each of those dipole fields is basically specified by the dipole vector m and the position of the magnet ri. So all we need to do is like figure out where do we want to put the magnet, specify the position, and with what dipole vector should, like which way should that dipole vector point, and with what magnitude. Those are the optimization variables. There's a lot of like secondary and tertiary requirements. You want to use as few magnets as possible. That's where the sparsity comes in, because you don't want to like use way more magnets than you actually need to like make the magnetic field of this thing. You want the magnets to all be maximum strength. You don't want the like 100,000 magnets with 10% of their strength. You want 10,000 magnets with all of their strength. And again, that's sort of a sparsity requirement. And you also typically only want magnets that point in particular directions. This just makes it easier to like build these things in practice. If you let these magnets like be in any possible direction, it's just really, really challenging to build because these devices typically need like tens of thousands of magnets. So you don't want to make undergrads deal with that. So good, and so that's the setup. The optimization variables are going to be those dipole vectors of all d permanent magnets you want to place, and then the total field is just going to be sum all the dipole fields of all those magnets. Okay, and this is super high dimensional. The optimization problem boils down actually to something relatively nice, which is it says figure out what these dipole vectors should be. The requirement that you match the magnetic field actually turns into a linearly squared term in the M, which is really nice. And notice we have an L0 term on the M, so that's enforcing the sparsity. And in fact, we also have some constraints on the M's that just caps them at a certain strength, because you can only get so much field from these permanent magnets. And yeah, just to remind you again, so this is sparse regression, and one of the big challenges of it, so not only are we doing L0 norms, so it's non-convex, non-smooth, but the problem is extremely high dimensional. We have 226,000 optimization variables, a third that many constraints. So this is just like, you can't possibly hope to solve this exactly. And I'm going to show greedy algorithms actually work quite well with it. Okay, just a reminder, greedy algorithms are sort of what they sound like. You iteratively determine optimization variables. It's super efficient, but it's super risky. And the way to see that it's risky is to look at how you greedily sum nodes in a tree. And so you start at 7, and you say, okay, if I want to maximize the sum, what I should do between 3 and 12 is I should add 12 to 7. And then so forth, I should add 6, I should add 9, and I get a total sum. I don't want to do the math. But the point is, if you had not done this greedily, you could have figured out that actually by first going to 3 to 1, get down to 99, and that would have really done a lot better in terms of maximizing the sum of those numbers. Okay. This is like sort of a worst case scenario. Like greedy algorithms are absolutely terrible for like tree structures. But this sort of shows you the pitfalls. However, it actually works really well for these magnet problems. I can talk a little bit about why that's the case. I think we have some understanding there. But one big benefit also is the efficiency is really good. As I said, this is like 10 to the 5 variables, but you can run this on like 5 minutes on a supercomputer these days. So you get a lot of efficiency benefits. Here's what one of these solutions look like on one of these accelerators. I'm showing the plasma surface is sort of like underneath the magnets that you're looking at. It's in like yellow and purple and green here. And then I'm showing the solution with the magnets with either plus or minus the maximum strength in blue and red. And you'll see there's some like gray whitish spots in the grid. That means no magnet was placed there. So there's this big grid where you're allowed to place magnets, but you want to place as few as possible. So not all the magnets get put down. Okay. So this is roughly what a solution looks like. And you'll see there's, when you do these greedy algorithms, you often get these like suboptimal solutions where you get isolated magnets where one magnet is right next to another magnet with exactly the opposite sign. So they're actually essentially canceling right there. So those two magnets are essentially worthless. And you can actually go and add what we call backtracking to these algorithms to sort of like look around your solution, find these bad magnets and take them out of the solution, and then keep optimizing after that. So it's sort of like a cleanup process every once in a while in your algorithm. And that actually works really well. So that's sort of how we deal with some of this suboptimality from using greedy algorithms. And we've been playing with this a lot. We even have tried these like hybrid algorithms. We use some amount of continuous optimization, some amount of greedy optimization. And there was this proof of principle project a few years ago. And our latest techniques, we can actually get the same performance as the original, but use 30% fewer magnets. That means literally like 10,000 less magnets. So especially for these high dimensional problems, doing the optimization well like really matters. It really can make a huge difference in solution quality. This is the original solution they got, and this is the solution we get after our algorithm. And if you sort of flip it between the two, you can see big chunks of magnets get chopped off. Okay. And yeah, just to summarize, the original solution they designed had 35,000 magnets with about the error in the magnetic field on the surface was 12 times 10 to the minus 5, some units. And if you do this like mixed, continuous, and greedy algorithm, you can actually, sorry, really greedy continuous works better. You can reduce the magnets by over 10,000 and get essentially the same errors. Okay, yeah, I just have a few minutes left that I'll talk about some of the other highlights. Another thing we've been working on is instead of magnets, actually using just like little dipole coils and just letting them rotate. So trying to control the currents and the orientations of all these little coils, and it's a similar problem. You start with like a lot of these little coils all around your plasma, and you start chopping these. We actually use a form of nonlinear sequentially thresholded least squares, and you often can like chop something like half the coils and get essentially the same errors. So when you first start, it looks like all the coils, like not all the coils are really contributing very much, and you can sort of sequentially threshold those in a sort of similar fashion to some of the sparse regression problems in system identification. And just to show you the sort of progress of the algorithm. So solid blue line here is the main error, the magnetic field error on the surface. And the solid red line is the number of coils. And what you can see is basically as this thing progresses, even around here, where you've gone down from like 100 coils to something more like 70, 60 coils, the error basically has integrated more than like factor of 2, something like that. And actually we're doing this thresholding and slowly raising the threshold as we solve. So this is sort of a sparse regression way to sort of get essentially the same solution as before, but cut down the number of coils you need by at least a factor of 2 or something. And that really helps with like, yeah, just reducing the complexity of the final solution at the end.
Question on Zoom.
Oh yeah. Mm-hmm.
Is the planning to keep the algorithm effectively parallelizable?
Yeah, it is because functionally, each iteration is just like 2 matrix vector products, which are just like trivially parallelizable. The slower part is when you do a backtracking to like check your solution, but we only do that every like few hundred iterations. We don't have to do that every iteration. Yeah, so yeah, the greedy algorithm is really, really fast because of that. And the reason it runs so fast on a supercomputer is we wrote it in C++, parallelized it with OpenMP, then did even fancier stuff in Xsimity to like put multiple things in a cat. Like we really probably overdid it, but it's very fast because of that. Okay, and last thing I want to talk about is designing coils with these like finite element style solutions, where you basically just initialize like a bunch, again, a 3-dimensional grid around the plasma. You say currents can flow in that grid, and then you just try and sparsify those currents to try and get something that looks like coils in the end. Okay. So once again, you can use these sparse regression algorithms. this, if you've seen finite elements before, this is sort of like a finite element-ish way to design coils, but with the addition of trying to optimize it with these sparse regression techniques. And so when you take this thing and when you add sparsity, you end up getting solutions like this. So you cut away a lot of the currents and you end up getting these solutions at the end that look a lot like what you would expect for this torus, just axisymmetric coils.
In this example, is it group sparsity based on like axisymmetry, or is it discovers the axisymmetry?
Yeah, so that's a nice thing. Yeah, it discovers the axisymmetry because the best solution is going to be axisymmetric for the torus. And if you just chop away at this thing, it just gives you axisymmetric coils. We do actually use group sparsity for this, but that's actually to enforce like a current conservation in each of the voxels. You have to be a little careful here because you need like div j to be zeroed globally, and that gives you a requirement on like how much current is flowing into each voxel. So you have to be a little careful there. Okay, that's it. That's what I wanted to share today. I put up some other things I'm working on or more likely want to work on, but haven't had time yet. Thanks, everyone.
So why do greedy algorithms work well in this case?
Yeah, they work well in this case because there's a clear way to like address the suboptimality. The suboptimality is both obvious and addressable. So like the primary way your solution is suboptimal is you have two magnets that are assigned near each other. And it's also easy to fix that, which is you take both magnets out. But that's just like a lucky aspect of this problem. If these were coils instead of magnets, that is not the case. Because then exactly what the coil fields are is like a complicated, it's a more complicated function because it's not just are two coils next to each other but oppositely oriented. It's also, do they have the same current going through them? So it's like a lot harder to tell like when two coils can be like removed from a greedy solution. So yeah, this turns out this problem is just like really nice for greedy problem for a greedy solution. Question? Yeah.
How much versus like looking ahead one step? So if we think of greedy just being the next node on the tree, if you went an extra layer down.
Yeah, we haven't looked at it. I mean, so we've done something similar in spirit, which is we've also tried these greedy algorithms with, instead of you placing one magnet at a time, you place 5 or 20 magnets at a time. And then you are looking for sort of like, yeah, what's the next step I could take placing 20 magnets that most reduces my error? That does tend to work pretty well. And it also, yeah, it tends to work pretty well. You do have to make some choices, like when you place 20 magnets, typically we place them all with the same like orientation, because otherwise you also have to worry again about like oppositely oriented magnets, do backtracking. So yeah, it's a little complicated, but we've tentatively looked at that. We've also done a lot of scans of like, if you don't just remove magnets that are exactly oppositely oriented, but maybe like they're just kind of like somewhat or oppositely oriented. And it turns out for a lot of these experiments, you do want to backtrack pretty aggressively. Like not only when they're 180 degrees to each other, but even when they're like a little bit over 90 degrees, you can see benefits from backtracking. Yeah.
So you mentioned the topology-based sparsity. Was all of this L0 based sparsity, or was any of it topology?
Yeah, so it was all L0 based. Even the people who do topology optimization, they need to solve a relaxation of the problem. And the way they do that typically is something called the density method. And for folks who don't know, that basically means you sort of like normalize your variables to 0 and 1. And then you just, instead of like demanding your variables are discrete, 0, 1. You allow them to be continuous, but then you add a term in the optimization. This is not whiteboard here. You add a term in the optimization that looks like alpha times 1 minus alpha. And what that function looks like is it's peaked at 0 and 1, and it's very like flat and towards 0 in the middle, and that preferences the solution to be towards 0 and 1. And this works pretty well, but it has the same problem as a lot of other algorithms, which is things like pile up at 0 and 1, but they're not exactly 0 and 1. So it really is like an approximation of the discrete problem. And then you have to do extra steps like thresholding or like chopping off those that like pile up near the edges. So yeah, so people have tried topology optimization actually for this permanent magnet problem, and it performs similarly, but there's like a lot actually in common about like you have to threshold, you have to backtrack, you have to do a lot of this stuff. Yeah.
So it looks like, sorry, the plasma isn't changing here.
Yeah.
In the future, is there going to be a need to have coupling between these optimizations and the actual physics?
Yeah, I was thinking about adding a slide about that, but we're currently so folks these days have been working on what they call single stage. I don't know why. Anyways, it's where you're allowing the plasma to vary at the same time you're allowing the current sources to vary. The much more challenging optimization problem because there's complicated coupling and the plasma is doing all sorts of weird things. And we are actually working on a version of this that does like this single stage with permanent magnets or with these dipole coils. Yeah, and actually it's a really good thing to do because often what you want is not only for your coils to match the plasma, you want the plasma to be like a plasma that is easy to make with coils. And that's something that you can only do by like combining the optimizations.
Cool.
Yeah.
Which may be a bit more prosaic, but how do you get the energy out of nuclear? Like,
Yeah, see how short I can make this. Yeah, so
because like all these things, whether it's the stuff to initiate the plasma, like it takes up space in
yeah,
the containment.
it's an
where you-
extremely crowded area. Yeah. The way is the plasma gets super hot, it starts fusing. What you get out of that is you get an alpha particle, which is just like a high energy charged particle, and that like heats up your plasma, and you can extract that heat by just like every once in a while like sort of sweeping your plasma into a trash can called a diverter. And that gives you a fair, you can basically run some water over that thing to cool it. The water heats up, you spin a turbine, you get the energy from it. That doesn't give you much of the heat. Most of the heat in fusion comes out as neutrons. And the problem with that is that neutrons just fly straight out of your machine, and it's really hard to like get that energy out. And so what you have to do is surround your whole device with a gigantic thick lithium blanket, which is makes it very crowded. But the advantage of that is then neutrons fly out, they hit your lithium blanket, they undergo a reaction that releases energy, and you can cool that blanket, and again, water heats up, you spin a turbine. Okay, so that's how you get the energy from the neutrons. And it's doing something even more complicated, which is as it's doing this, it's breeding isotope of hydrogen called tritium, and you need to put that tritium back in the device to keep the fusion happening. So yeah, it's a long answer.
But in terms of so that's great to know. And then in terms of like the control, like 'cause you talked about active control, part of that is okay, plasma, go to the diverter now.
Yeah, really,
Come back from the diverter.
really, it's getting continuous. The edge of the plasma is getting continuously swept into these diverters at all times. But exactly where like the strike point is on the diverter is extremely important for the amount of like heat flux hitting that plate. So like doing tiny active control to like really precisely control where the plasma hits that is really important. So there's things you want to do in terms of active control there. Fortunately, the problem is extremely complicated near the diverter because your like plasma is like smashing into this thing. It's a plate, so like neutral atoms are getting recycled back up from the plate, and neutral atoms, when they get smashed, start to radiate extremely hard. So there's like it's just an absolute disaster near the diverters. But yes, we would like to control it around that.
Mark Ivanovic is asking, how have you considered augmenting the optimization problem in the equilibrium physics, or is that better solved as a separate problem?
Yes, so this is exactly the question of doing two stages or doing a single stage. So do you first like optimize the shape of this plasma and find like a really good plasma with good properties that you want? And then you say, okay, given that good plasma, let's find some coils and current sources that can create it in practice. And that's sort of, you do one optimization, then you do a second optimization. But in principle, you could do them at the same time. You could say, you could let the plasma shape vary and let the current sources vary, and try and optimize both for good plasma and good coils at the same time. This is a really good idea. The downside is it's an extremely complicated problem. When you write down the full problem, you know how I showed those objective functions with like secondary, tertiary, etc. The full problem is like 15, 20 terms. And each of those terms has weights. And you have to fiddle with all those 15 or 20 weights and hope that you get a good looking solution. And because it's non-convex, it's extremely sensitive to the initial guess you give it. So it's an extremely challenging problem, but we would like to get better at it. So it's one of the things I'm interested in. Yeah, good question.